Right now, if you just go outside and stand on your front lawn, sitting exactly 6 feet beneath the grass, there is a massive untapped battery.
Yeah, it's pretty incredible to think about.
It is, and it's holding this perfect, steady temperature of roughly 60 degrees, and it has literally been sitting there since the day your house was built.
Just waiting to be used.
Exactly. But, when most of us hear the word geothermal, we instantly picture something, well, incredibly exotic.
Right, like sci-fi stuff.
Yeah, we imagine this heavy crew drilling for crude oil next to the driveway, or, I don't know, tapping into some roaring, steaming volcanic geyser right under the patio.
Which would be terrifying.
It sounds loud, it sounds dangerous, and it sounds like something reserved for a mad scientist's lair, not a standard suburban home. So, welcome to this deep dive into the sources. Our mission today is to completely demystify geothermal heating and cooling.
Which is much needed, honestly.
We're going to strip away all those exotic sci-fi associations and look at the brilliant, quiet physics of what is really happening beneath the topsoil.
Because the reality of this technology is remarkable, mostly because it relies on this profound simplicity rather than, brute force.
Right.
And we're working from some fantastic source material today. We have a collection of field notes, technical specs, and insights from Dave Hartzell.
Yeah, and he's an IGS-HPA accredited HVAC master, right?
He is. He's been running a family business in Oklahoma for 47 years. And when someone has nearly 5 decades of hands-on experience in a trade like this, they really stop focusing on the flash.
Yeah, absolutely.
They focus entirely on the physical realities of what actually works year after year, decade after decade, in some deeply unpredictable weather.
So, okay, let's unpack this. Because reading through Dave's insights, I immediately realized my mental image of geothermal was just entirely wrong.
Most people's are.
If there are no volcanic geysers and there is absolutely no magma involved, are we just burying a glorified garden hose in the dirt? Like, how does a plastic pipe sitting in the cold mud replace a massive roaring gas furnace in the dead of winter?
To understand that, we have to kind of completely change how we think about the whole concept of heating and cooling in the first place.
Okay, color me intrigued.
Before we even look at the machinery, we have to look at the environment that the machinery operates in. The fundamental flaw with traditional HVAC systems, your standard outdoor air conditioner or your furnace, is that they are hopelessly dependent on the outside air.
Right, which is always changing.
Exactly.
Yeah.
The atmosphere is incredibly volatile. If we look at Dave's environment in central Oklahoma as our primary example, the air temperature is absolute chaos.
Oh, yeah, the Midwest swings are brutal.
It can plummet into the single digits during a brutal January cold snap and then swing to well over 100 degrees in the scorching August sun.
And that volatility hits exactly when you need your system to work the hardest. Like when it's freezing outside, you need the heat on full blast, and when it's boiling out, you need the air conditioning running nonstop.
Yeah, and that volatility is precisely what breaks traditional systems down. They are fighting a constant uphill thermodynamic battle.
It's basically a tug of war.
Yes. Think about a traditional air conditioner in August. It is trying to take the heat from inside your house and dump it outside. But the air outside is already 100 degrees.
Right, there's nowhere for the heat to easily go.
It is like trying to sweep water uphill. It takes a massive amount of electricity to force that heat out into an already sweltering environment.
That makes total sense.
But if you walk out to the yard and dig down just a few feet, getting below the frost line, the environment completely changes. The Earth just sits there, completely isolated from the atmospheric weather above.
It's just insulated by itself.
Exactly. Year-round, depending on the exact depth and your geographical region, that dirt stays at a calm, stable temperature, usually in the high 50s to the mid-60s. And what's fascinating here is that a geothermal system doesn't try to fight the extreme, volatile air.
Just ignores it.
Completely ignores it.
Mm-hmm.
Instead, it partners with the steady, reliable temperature of the ground.
Okay, I am following you on the stability part, but let me push back on the numbers for a second.
Sure, go ahead.
Because if the ground is only sitting in the high 50s or mid 60s, how on earth does that keep my house warm during a January blizzard? 60 degrees sounds absolutely freezing when I'm just trying to sit and watch TV in my living room. I mean, most of us want our houses sitting at a comfortable 72 degrees, right?
Oh, absolutely. That gap in temperature is the most common hurdle people have when trying to wrap their heads around geothermal. And it brings us right to the actual mechanics of the thing.
Okay, hit me with the mechanics.
We need to look at how a single buried pipe handles two completely opposite seasons. Let's break down the physics, starting with the summer. because dumping heat is a bit easier to visualize.
Yeah, summer makes sense.
In the summer, your house is full of unwanted heat. Instead of an outside AC unit trying to blast that heat into the 100-degree air, a geothermal system pulls the heat from your house into a fluid circulating through a buried loop of pipe.
And according to the source notes, that fluid isn't anything crazy either. It's just water mixed with a little food-safe antifreeze. Right.
Yep, just water and a benign antifreeze. So the system pumps that warm, heat-laden fluid down into the ground. Because the Earth is sitting steadily in the low 60s, it is vastly cooler than your hot attic and much cooler than the sweltering outside air.
Okay, so it just naturally wants to shed that heat.
Right. Nature abhors a differential, so the Earth acts as a massive heat sink. It readily absorbs the heat radiating through the walls of the pipe. The fluid rapidly cools down in the dirt, comes back up to the house, absorbs more heat from your living room, and just repeats the cycle.
So in the summer, you're basically taking the unwanted heat from your living room, carrying it outside in a fluid, and burying it in the yard.
The yard literally becomes your heat trash can.
I love that. A heat trash can.
But now, for the winter, the system runs exactly backward. This is the mechanism that answers your question about how 60-degree dirt can heat a home.
Right, because this is where the math wasn't mathing for me.
So in January, the air outside might be 10 degrees, but 6 feet down, the ground is still holding on to that 60-degree warmth. The fluid circulates down into the loop and absorbs what thermodynamic engineers call low-grade heat from the Earth.
Okay, low-grade heat.
Yeah, and the fluid comes back up into the house carrying that 60-degree energy.
But again, 60 degrees still isn't warm enough for my living room. Like, we are still 12 degrees short of comfortable.
And that gap is bridged by the heat pump itself using a refrigeration cycle. And this is where the physics are truly brilliant. The indoor unit takes that 60-degree fluid from the ground and passes it over a heat exchanger.
Okay.
And this heat exchanger is filled with a specialized liquid refrigerant. Now, the key to this refrigerant is that it has a boiling point that is incredibly low, often well below zero.
Oh, wow. Below zero.
So to this extremely cold refrigerant, that 60-degree water coming from the yard feels like a blazing fire.
That is wild to think about.
The heat from the water causes the liquid refrigerant to immediately boil and turn into a gas, capturing all that low-grade energy.
Wait. So the refrigerant boils at a negative temperature just from contacting 60-degree water.
It does. Phase changes are powerful mechanisms for trapping heat. Once that heat is trapped in the vaporized refrigerant, a mechanical compressor powered by an electric motor takes that gas and physically squeezes it.
Squeezes it, like compressing the gas.
Exactly. Think about a manual bicycle pump. When you pump a tire vigorously, the metal cylinder of the pump gets remarkably hot in your hands, right?
Yeah, it does. I've noticed that.
Compressing a gas forces the molecules closer together, which causes the temperature to rapidly spike. When the compressor squeezes that vaporized refrigerant, the temperature shoots up from 60 degrees to well over 100 degrees.
Oh, so you're forcing it to get hot.
Yes. And then a fan blows across those incredibly hot coils, sending warm, comfortable air into your ductwork. The system is not creating heat from scratch like a gas furnace does by burning fossil fuels. It is simply harvesting the existing heat from the ground, changing its phase, and compressing it until it's hot enough to use.
You know, here's where it gets really interesting. Because the way you're describing this phase change in the fluid loop, it's literally a thermal sponge.
A thermal sponge, I like that.
Yeah. In the summer, you're soaking up the house's heat and wringing it out into the cold dirt. In the winter, you're soaking up the Earth's natural warmth, bringing it inside, and letting the heat pump compressor squeeze it until the temperature concentrates and becomes hot enough to warm the room.
The thermal sponge analogy captures the physical transfer perfectly. You are simply moving energy back and forth from a massive reservoir rather than generating it from combustion.
Which has to be so much more efficient.
That transfer process is exactly why the efficiency ratings on these systems are incredibly high compared to traditional heating.
So now that we have the thermal sponge mechanism down, how is this actually built? Because the source notes talk about different ways to physically put this pipe in the ground.
Yes, the installation side.
Right. And I'm looking out at my quarter-acre suburban plot, and there is zero chance you're fitting miles of pipe under my azalea bushes without destroying the neighborhood. What is the physical setup for someone without a massive farm?
The notes from Dave highlight two main categories of installation: closed loops and open loops. Let's start with closed loops, which they really dominate residential settings.
Okay.
Closed
A
loops.
closed loop is a completely sealed circuit of heavy-duty plastic pipe. The exact same water and antifreeze mixture runs round and round forever. This raises an important question because a homeowner's property size completely dictates the geometry of how that loop goes into the earth.
Geometry meaning how it's laid out.
Right. If you do happen to live on a sprawling piece of land, the installers can bring in a trenching machine and dig flat, horizontal trenches. They lay the pipe out in long, looping rows just a few feet down.
Okay, so just spreading it out wide.
Yeah, it requires a lot of surface area, but much less specialized drilling equipment.
But for the suburban plot, like the tight yards, for the suburban neighborhood with a tight yard, they rely on vertical bores. They bring a specialized drilling rig onto the property and go straight down.
Straight down like a well.
Exactly. We are talking boreholes that can go anywhere from 100 to 400 feet deep into the bedrock. They drop a U-shaped loop of pipe all the way to the bottom of that hole, pump it full of the fluid, and then completely seal the hole with a specialized grout.
Wow. 400 feet.
It takes up a fraction of the surface area, meaning they can install a massive closed loop in a tiny residential front yard.
Okay, I have to pause here on behalf of anyone listening who is highly protective of their property and their community.
That's fair.
Because if I have this massive closed loop of chemical fluid running deep into the bedrock, potentially hundreds of feet down, what happens if it springs a leak? Like, if a pipe cracks, am I pumping antifreeze directly into the neighborhood's drinking water aquifer?
The environmental concern is completely valid, which is exactly why the industry standards are so rigorous. As Dave's notes explicitly point out, the antifreeze used in these closed loops is propylene glycol.
Propylene glycol.
Yes, and it is strictly food safe. It is the same benign additive used in many foods and cosmetics. In the incredibly rare event that a subterranean pipe is compromised and the fluid leaks, you are not contaminating the water table with toxic chemicals. It breaks down safely.
Oh, well, that is a huge relief.
But for property owners who want to avoid circulating antifreeze altogether, there is the other option, the open loop.
Okay, so if the closed loop is a sealed circuit, how does the open loop change the equation?
An open loop doesn't circulate a captive sealed fluid. Instead, it relies on an active groundwater source. It pulls water directly from an existing high-capacity well on your property.
So it's just pulling raw well water.
Right. It brings that 50 or 60-degree well water straight into the house, passes it through the heat exchanger to extract or deposit the heat, and then safely discharges that exact same water back into the earth, usually through a secondary return well located further away.
That sounds even simpler. You just use the water already down there.
It is incredibly efficient, but it comes with a major caveat. It heavily depends on the groundwater quality.
Oh, like mineral buildup.
Exactly. If your well water is highly acidic or full of dissolved minerals and iron, it acts just like hard water in a coffee maker.
And nobody wants that in their expensive HVAC unit.
Definitely not. Over time, those minerals will calcify and scale up the delicate internal plates of the heat exchanger inside your unit, eventually destroying it. That is why veterans like Dave lean heavily toward closed loops. The sealed fluid is perfectly clean, highly predictable, and it places zero burden on your local well water supply.
Let me bridge these two concepts, because if I'm opting for that vertical or horizontal closed loop to protect my groundwater, I'm basically wrapping a thick plastic barrier between the circulating fluid and the raw earth.
Yes, the pipe itself.
Doesn't that high-density plastic act like a wall? I mean, how does the heat actually cross over from the fluid through the plastic and into the dirt efficiently?
That transition from the pipe to the environment is the most critical variable in the entire system. We have been talking about the pipe itself, but the soil holding the pipe ultimately dictates whether the thermodynamics will actually function. Soil composition changes everything.
Dave uses his local Oklahoma dirt as the prime example in his notes. He mentions that digging in clay is completely different from digging in sand.
The physical properties are fundamentally different. If you think about clay, its primary characteristic is that it holds moisture tightly. It is dense and damp.
Right, it's heavy stuff.
And from a thermodynamic perspective, moist soil conducts heat remarkably well. Water is a great conductor. Conversely, dry, loose, sandy ground is full of tiny air pockets.
And air is an insulator.
Air is a terrible conductor. It acts as an insulator. If you have a pipe trying to pull heat out of the earth in the dead of winter, damp clay is going to transfer that heat into the pipe much faster than dry sand ever could.
But looking at the source notes, they really emphasize this specific IGSHPA accreditation, the International Ground Source Heat Pump Association.
Yes, IGSHPA.
If the soil conductivity is just a natural property of the yard, why do installers need specialized accreditation? I mean, can't any guy with a rented backhoe and a spool of plastic pipe just bury a loop, cover it with whatever dirt is there, and call it a day?
Oh, if you hire the guy with the rented backhoe to just bury a pipe, you are almost guaranteed a catastrophic and expensive failure.
Oh, wow, really?
Yes, because while clay is great for transferring heat, it also shifts, expands, and packs down unevenly. When the trench is backfilled, ensuring there is solid, continuous, compacted contact between the plastic pipe and the soil is paramount.
So no air gaps.
Exactly. If the backhoe operator leaves gaps, clods, or air pockets around the pipe, those air pockets insulate the pipe. Your thermal sponge is suddenly wrapped in bubble wrap, unable to absorb or release heat.
So the installation method dictates the thermal contact.
Yes, but the accreditation goes much deeper into the underlying math. Loop sizing is a strict, unforgiving thermodynamic calculation.
It's an exact science.
An IGSHPA certified installer has to calculate the exact heating and cooling load of your specific house down to the BTU, and then they have to factor in the exact thermal conductivity of your specific soil. They use those variables to determine precisely how many hundreds of feet of pipe are required to meet that demand.
So what happens if they get it wrong? Like, let's say a DIY installer puts too little pipe in dry, sandy soil to save a few bucks.
Well, let's play that out. The heat pump turns on in January and begins extracting heat from the fluid to warm the house.
Right.
But because the sand is an insulator, it doesn't let the deeper surrounding earth replenish that heat fast enough. The pipe is extracting heat faster than the earth can supply it.
Oh, no. So it just gets colder and colder.
The fluid in the loop gets colder and colder, dropping well below freezing. Eventually, any trace moisture in the soil immediately surrounding the pipe freezes solid. You have literally created a perpetually expanding underground glacier in your front yard.
An underground glacier? That is insane.
Once that soil freezes into an ice block, thermal transfer stops completely, the system shuts down, and your house is freezing on the coldest day of the year.
And I imagine you can't just climb into the attic with a wrench to fix an underground glacier.
No, you definitely cannot. Unlike a traditional furnace where you can just swap out a faulty igniter or a bad fan motor, if your buried loop is mathematically undersized, the only fix is heavy excavation.
You have to dig it all up again.
You have to bring the heavy equipment back, tear up the yard again, and bury more pipe. It is astronomically expensive to fix a thermodynamic mistake once it is buried under 6 feet of dirt.
So, given all this intense engineering, the heavy excavation, the unforgiving math, the soil conductivity analysis, I think a lot of people listening might be wondering, is all this upfront disruption actually worth it? You are tearing up your landscaping just to bury plastic.
The heavy upfront disruption makes sense when you evaluate the lifespan and the ultimate payoff of the infrastructure. That underground loop is the longest living part of the entire HVAC system by a massive margin.
How long are we talking?
Decades upon decades.
Mm-hmm.
As Dave notes, the pipe they use is high-density polyethylene, or HDPE. And the most crucial detail about HDPE in a closed loop is how it is assembled. The joints of this pipe are not glued together with chemical solvents. They are physically fused using a specialized heating iron.
Oh, so what does this all mean? If there is no glue, it means there are no weak seams to crack under pressure, right?
Exactly.
It makes me think of welding steel. When you weld two pieces of steel properly, the joint becomes as strong as, or even stronger than, the original metal. By melting and fusing this plastic together, you're basically creating one continuous, unbreakable subterranean vascular system for the house.
You are creating a monolithic structure. When those pipe ends are melted and pressed together, the plastic cools and the molecular chains bind into a single continuous piece of material.
That's brilliant.
Because it is fused, there is no glue to degrade or get eaten away by the soil over time. Furthermore, because it is buried deep underground, the plastic is completely shielded from the primary things that destroy materials.
Like sun damage.
Ultraviolet rays from the sun, extreme wind, freezing ice, and physical weathering. The indoor equipment, the heat pump compressor sitting in your basement or utility room, is mechanical. It has moving parts.
Right, it's a machine.
It will eventually wear out and need service or replacement after a couple of decades, just like a high-end refrigerator. But that fused underground loop, it will easily outlast the mechanical equipment. It just sits down there, completely inert, quietly transferring heat for decades upon decades without ever seeing the light of day.
That is just Incredible longevity.
If we connect this to the bigger picture, it really highlights the overarching philosophy that a veteran like Dave Hartzell is getting at in his notes.
Yeah.
Human engineering often defaults to trying to overpower nature.
Yeah, brute force.
When the weather gets colder, we build louder, hotter gas furnaces to fight the cold. When the summers get more brutal, we build more aggressive, power-hungry compressors to fight the heat. Geothermal technology takes a step back.
It works with it.
Yes. It looks at the chaos in the surface atmosphere and recognizes that trying to fight it is a losing battle. It simply taps into the massive, quiet thermal battery sitting just beneath our feet.
It really is profound when you strip away the mechanics and just look at the relationship with the earth. For you listening right now, the next time you walk across a lawn or a city park, or even your own backyard, think about what is actually happening just a few feet below your shoes.
It's a whole different world down there.
You are walking over an incredible, massive resource. It is a perfectly stable reservoir of temperature, totally immune to the chaos of the weather above, just waiting to be tapped into with a brilliantly calculated piece of fused plastic. It makes you look at the dirt in a completely new way. It's not just soil, it's infrastructure.
It absolutely reframes our relationship with the ground. And building on that realization, I want to leave you with a concept that pushes this thermodynamic engineering beyond just a single suburban house.
Oh, I'm ready. What is it?
If one home can use the earth as a heat sink in July, and then successfully harvest that same heat back out in January, imagine what happens if we scale this mechanism up to a communal level. Think about a concept currently being pioneered called network geothermal.
Network geothermal. So instead of just my yard, we are linking entire neighborhoods together.
Imagine an entire city block networking their closed loops together into one massive, shared subterranean grid. Think about the commercial buildings in your town.
Okay, like office buildings and stuff.
Exactly, or a massive grocery store. A grocery store generates a tremendous amount of waste heat all year round, even in the winter, just trying to keep its massive banks of refrigerators and freezers cold.
Right, because refrigerators create heat on the back end to stay cold inside.
Right now, traditional commercial HVAC systems take all that waste heat and simply vent it up into the sky. It is completely lost. But what if that grocery store pumped its waste heat down into a shared community ground loop?
Wow.
The grocery store gets a highly efficient heat sink to keep its food cold, and the residential homes across the street can pull that exact same thermal energy out of the shared loop to warm their living rooms for free in the dead of winter.
That is genius.
It is a tantalizing glimpse into the future of urban energy. It transforms waste into a shared community resource, eliminating the need to burn fossil fuels, all facilitated by the dirt hidden right under the pavement.
So wait, my living room heat in January could be literally powered by the waste heat of the frozen pizza aisle across town.
Yes, exactly.
That completely breaks how I've always thought about the power grid and community resources. I mean, we have gone from picturing dangerous volcanic geysers to understanding a highly calibrated thermal sponge, and now to visualizing a shared underground energy network. It turns out the most exotic thing about geothermal heating isn't fire and brimstone. It is the quiet, brilliant physics of the dirt right beneath us. Thank you for joining us on this deep dive into the sources. Stay curious, and we will catch you next time.